Conservation of energy. So, conservation of energy, I want to do a problem. Just to start off with. I don't want to teach any new concept here because in the last lesson we actually nailed all the major concepts. I want to talk about a slingshot. And this slingshot is going to fire a 20.0 gram pebble vertically up. So we're shooting a stone straight up in the air. And at the time that it's at 4.00 meters up in the air, I want to talk about what's going on. It's traveling at 3.2 meters per second up. It's got an upward velocity. I'm trying to leave a little bit of time here to give people a chance to write. Now you watch this video later, maybe you fast forward a few seconds in advance and see where we are. But for now we're just going to leave a little dead air time. Everybody caught up? Alright. Alright, so let's draw a little picture here. Here's the ground. Here's a ball. You always want to accompany these things with diagrams. It's got a displacement from the ground of 4.00 meters. And at this particular point in time, it's got it, now this isn't an FED, this is just a velocity arrow. It's got a velocity of 3.20 meters per second up. And that's the story so far. Incidentally, if it's got a mass of 20 grams, what should I do about that mass before I go any further with it?
Find the force of gravity.
What's that?
Find the force of gravity.
Oh, we could find the force of gravity. What else could we do to it, even before we do that? Yeah, turn it to kilograms. How many grams in a kilogram? 1,000. Kilo means 1,000. So we could say that it's got a mass of, move that decimal place over once, twice, thrice, 0.0200 kilograms. Yeah, thrice is a word. Thrice. I don't know what you say for 4 times. Thrice, maybe. I have no idea. I have no idea what 4 times is. Maybe we just don't say that. Maybe we say 4 times. Here's part A. Part A. What is the total mechanical energy of the pebble at the time described? Okay, and when people say, what's the total mechanical energy? Well, what are the only 2 types of energy we've been able to calculate so far, in addition to work? We've done work, and what were the other 2? Kinetic, and not static, gravitational potential. But it's sitting still, I understand what you're talking about. Although it's not necessarily sitting still. Is this ball sitting still right now? But it does have a height, right? So it's got gravitational potential energy. So when people talk about total mechanical energy, let's just call it ET for, well, in the future we'll call it ET. Let's call it E total for now. Total mechanical energy. Total mechanical energy is that energy that's described by the energy it has due to its position plus the energy it has due to its motion. Okay? So we talk about EG, and there's other things we could throw into it as well if we're talking about elasticity and vibrational energy and all that sort of thing, but that's not where we're at right now. We're just talking about these particular parts of mechanical energy. So for our purposes, this is the total mechanical energy. Gravitational potential energy plus kinetic energy. And so I can say that at this moment in time, gravitational potential energy is equal to the mass of the object, we said this yesterday, times acceleration due to gravity, times its height above the zero height. No, the zero height is right down here, so it's 4 meters up, plus, do you remember what the equation was for kinetic energy? 1/2 m, yeah, 1/2 mv squared. That's not going to change, okay? So this is Eg, mass times acceleration due to gravity times height. Kinetic energy is 1/2 mv squared. So if I want to talk about its total mechanical energy, we can sub in some values here. So 20 kilograms. 9.
0.0200.
Oh, did you beat me to it already?
No, you put.
Oh, 20 kilo. Oh my gosh, what was I thinking? Oh, 20 kilogram pebble. 0.0200 kilograms. Thank you. I got carried away there. Times the height, 4.00 meters, plus 1/2. Oh, this big piece of paper really fits all my writing. That's nice. Plus 1/2 times, okay, 0.200 kilograms times 3.00. Oh, you caught me again. 0.200. 3.2 meters per second, and that value squared. Oh, I did it again. Okay, it's not a good day for me. All right. So we've got gravitational potential energy and kinetic energy. Let's do them.
20 kilograms in space right now?
Yeah, I wrote 20. I converted it. I changed it to 0.0200. I just messed up. We already addressed that, but I messed up. All right. Can I ask two people to do the calculation? Somebody find EG and somebody else find EK. Don't find them both together. Let's find them separately. Yeah, then we'll add them together. Yeah.
I got for the first one.
Okay, what'd you get?
First little section, I got 0.7848. So far.
Okay. So we got 0.7848 joules, and we can check to make sure that it is in fact joules. I've got kilograms times meter per second squared times meter, so that'll be meters squared per second squared times kilogram, and that's the definition of a joule. So yeah, the units all work out. Plus, does anybody get the kinetic energy for me? 3.2 squared. Don't forget to square the 3.2. 3.2 squared times 0.5 times 0.02. Somebody's got it. 0.1024. Any takers on that one?
Yeah.
Yeah, all right, we agree. The motion passes. And let's add them together. Can everybody see okay from where they are?
Yep.
Okay. Voice of the room. All right, what's the total mechanical energy? 0.87.
872.
872.
0.887.
Okay, got it. Joules. All right. Now, if we wanted to round this off to 3 sig figs, we could say that's approximately equal to 0.887 joules. So we could figure out the total mechanical energy, that is the gravitational potential energy plus the kinetic energy when it's at that height going at that speed. Okay? I'm going to take this away in a minute. Is there anybody that still needs the problem set up there? Speak up. Okay, it's disappearing. All right, I want to continue this problem. I want to continue this problem, and I'd like to call it a part B. So for the same problem that we had from previous, I'm going to make some notes about what we know. E total is equal to unrounded 0.8872 joules I'm just going to keep that as a note from before. Of course, on your page, you already have the information. And I'd like to say, what's the maximum height above the ground that this pebble can reach? So let's put it in writing. Microscopes. No, we don't have microscopes.
Okay, just trying to.
Sorry.
I had 30 and now it's 28.
There might be some in the center room there, but you probably already looked.
Yeah.
Yeah, sorry. Well, sometimes this room gets used for grade 9 and 10 science too. All right, what's the maximum height this pebble can reach? All right, so when you're throwing a pebble up in the air, you might imagine, we just talked about the point in time when it's here and has a velocity. Part way up, we'll say. But you know that when you launch something off of the ground, I don't know how this thing got launched other than it was a slingshot, but let's assume that the slingshot was on the ground when it launched. Would it have a greater velocity at the moment of launch or less, based on your understanding from projectiles? Greater, yeah. So it's going to be going pretty darn fast. Lots of kinetic energy and no gravitational potential energy. When it gets up to the very top of its motion, tell me something about the kinetic energy. Zero. But there's something that we've said before, and I'll say it again. Conservation of energy, or the law of conservation of energy, says that energy is neither created nor destroyed, it just changes form. Yeah?
Does that mean that it's going to be 0.872 or so? So it all has to be gravitational?
Yeah, you got it. Okay, it's just transformed into other types of energy. Somebody just delivered a slinky. That's fun. It's a slinky in a can, in a beaker. They're doing a slinky experiment. Yes, you can in the sound unit. Absolutely. No, we're not doing it right now. All right, so we're going to say that energy gets transformed into different forms, and Chris already said that means that if we start out down here with E total being EG plus EK, and we get up to here, E total is still EG plus EK, and we get up to here, and E total, same old, is just EG plus EK, we can start talking about some critical things that happen at these three different time intervals. At the first time interval, the gravitational potential energy at the ground is equal to what? Zero. So that means the total energy, and we calculated that to be 0.8872 joules, is all wrapped up in kinetic energy at the start. Here, is there 0 EG or 0 EK? Because it's in motion and it has height, so we have to deal with both of them. Up at the top, something critical happens. Which thing becomes 0 at the top? EK. So all of your energy is wrapped up in what type of energy now? Gravitational potential. Okay, so if I want to know what the maximum height is, you guys tell me. What do I do? What kind of an equation could I use? E total equals what? This one, or this one? E total equals EG, yep. E total equals EG at the top. If I want to be really expressive, I can write plus EK and then say, oh yeah, by the way, I know that EK is equal to 0. And I can say that E total is equal to I'll sub in the whole value for EG. Mass times acceleration due to gravity times displacement in the y direction from the 0 height, which was down here. And I can isolate for delta dy. I can say delta dy is equal to E total divided by mass times acceleration due to gravity. And I can start plugging in my values. E total, 0.8872 joules. The mass was little, 0.0200 kilograms times acceleration 9.81 meters per second squared. And I forgot to make a note, this just carries over from part A that mass is 0.0200 kilograms.